Hey everyone, welcome back to my channel. So in this video, our task and our data set is exactly the same as in the last video, which is an electricity production from renewable energy resources in Romania from 2019 to 2023. And we want to do long-term forecasting, which is forecasting the electricity production from October to December 2023. So we have around 2,000 values to be predicted. That's why it's called long-term forecasting. But the model now is different. We're going to study NBEATS, which is the president of NBEATS. And then we will apply that and see how the model goes. Okay, let's study together. So NBEATS is the precedent of NHITS. In other words, NHITS was built upon NBEATS. So we will, if you have seen that video, you will see that NBEATS is really similar to NHITS. Okay, but for today's video, we're going to learn NBEATS, which stands for Neural Basis Expansion Analysis for Interpretable Time Series Forecasting. Okay, I guess, well, time series forecasting is obvious. And then for the neural one, it's also obvious because it's a neural network. More specifically, it's an MLP-based neural network. So we just use the fully connected layer and expand that to build a huge model. And we will see that in addition to the fully connected layer, we will also have basis layers. That's why we have the basis word here, basis expansion. Okay, we will see that. Now let's look at the model, the full model first. So the model consists of several stacks, and each stack has several blocks, each of which has some fully connected layers, and this one is the basis layers. This is our basic block. So each block has two parts. The first part covers this part, the MLP stack and the linear layer, which generate the expansion coefficients denoted by theta. And then the second part is at the bottom of the block, which are the basis layers, and these generates the forecast and backcast. Okay, so each block gets one input and generates two outputs, the forecast and the backcast. Now let's look at the first part of the block first. This is MLP stack here. It means it's a fully connected layer network with several hidden layers. And the activation function of that is ReLU. So more specifically, it would be the ReLU function of the weight learned by the layers times x. X is the input. Sorry, I mean x like this. And then plus some bias. Okay, and then the output of the MLP stack will go into two different layers. Both are linear functions. Actually, not linear functions, but still a fully connected layer. But the activation function is linear function. Okay, and the output of that would be the theta, the coefficient for the expansion. So theta f, let me erase the inks. Okay, theta f of block L means that it's the expansion coefficients for the forecast, while theta b, the letter b here, denotes the backcast. Okay, so once again, the block input goes into the block and then goes through fully connected layer stacks and then goes to two different places and we get the theta. So in the next part, we use expansion coefficients in the basis functions to generate the forecast and the backcast. Now, NBEATS provide two types of architecture. The first one is the generic one and the second one is the interpretability architecture. And the difference between them is in the basis functions. So in generic function, wait, let me go to the slide of this one. The generic one, with the generic architecture, the basis functions are learned automatically by the network. while in the interpretable architecture, the basis functions, we have two basis functions, the trend and the seasonality. So the idea is that we want to make the result human interpretable. That's why we sort of like decompose the time series into two components, trend and seasonality. For the generic architecture, this is the basis function. So here we can see the theta, and then v is the basis function. So v, both for y hat and x hat. Y hat is the forecast, while x hat is the backcast. Okay, so the dimension for v, both for forecast and backcast, would have the dimension of the horizon. The horizon is the total values that we want to predict times the dimension of, or the length of the expansion coefficient. Well, I guess I should write it as dim for dimension of theta. So we can think of the columns of matrices V as the waveform. That's why the result would not be able to be interpreted. Okay, whereas in the interpretable architecture, we would have trend basis and seasonality basis. The trend basis means that the model has to mimic the trend component of the time series, whereas in the seasonality, the model uses Fourier periodicity. Okay, so I have to elaborate this one. In the building basic block earlier, the basis layer is written as like this: g of theta. Theta is the expansion coefficient. And then in the generic architecture, g of theta becomes v times theta plus some bias. So in the generic architecture, g, or the function of theta, is v times theta plus b. But in the interpretable architecture, we have two basis functions. The first one is trend. If we are using trend, then it's a polynomial function. The degree of the polynomial function would be 2 in our case. We will see in the coding section that we will set the degree up to 2. And then for the seasonality, it would be a periodic function using Fourier series. Okay, so that's what happens in each block. Now let's look at the model from the stack level. So each block would have forecast and backcast, right? The forecast will be aggregated to make the stack forecast. And then later, all the stack forecasts would be aggregated for the global forecast. For the backcast, though, it's a bit more complicated. The backcast is used to be subtracted from the block's input. And the residual of that, so the difference between the block's input and the block's backcast, would be used as the next block's input. So the stack input goes through block one, sorry. And then the block one has the forecast, which is here, and then the backcast. Let's say the backcast is here. And then this would be subtracted from the block input, which is this one. Okay, and then the result of that goes to the block 2. And then similarly in block 2 receives an input here, and then it will output a backcast. The backcast of block 2 would be subtracted from the block 2's input, which is the residual of block 1. Okay, and so on like that. So if we see the full model again here, each stack has its own block, right? So maybe we can draw the blocks like this. The very first block, so block 1, stack 1, this particular block, would receive the raw input time series, while the rest of the blocks would receive the residual. the time series would have one component removed as we go through the blocks. So let's say that we have an interruptible architecture for simplicity. So we just use stack 1 and stack 2. Stack 1 is the trend. Maybe I should erase the inks first. So if you're using the interpretable architecture, we would have 2 stacks only. So we don't need the rest of the stacks. And then stack 1 would use the trend basis, while stack 2 uses the seasonality basis. And then let's say that we have 2 blocks. Actually, in the paper, they say that they use 3 blocks in each block. So yeah, I'm going to draw 3 little squares here. So after, this is the raw input, okay? So, and then the input goes through the trend stack. And then coming out of the trend stack is the time series with the trend component removed. In other words, detrended time series. So the time series that goes to the seasonality stack would have, well, presumably would have only the seasonality component and white noise. So that's the basic idea of NBEATS. If you want to know more about this, you can read this paper. This is the official paper of NBEATS model. So here we are now in our Kaggle notebook. First, let's install the library that we're going to use to apply NBEATS, and that is Neural Forecast for this particular video. After that, we will import the libraries, the basic ones like NumPy, Pandas, and Matplotlib. And then to implement NBEATS, we will use NBEATS and import it from Neural Forecast.models. And then as a measurement for the model performance, we will use MAE, and we import it from Neural Forecast.losses.pytorch. I also need to import torch because later when we calculate MAE, we need to put in 2 torch tensors. That's why I need to convert a NumPy or Pandas series, if I remember correctly, Pandas series to a torch tensor. Okay, let's run this. Okay, we have 1 dataset only, and now let's load it. The date time is already parsed as dates, and then in this dataset there are some duplicates. That's why I have to drop them. And here are the first few rows of the dataset. As you can see, the first column here is the time index, and these are the hourly time index. And then the next column is the consumption, electricity consumption, and then electricity production. This is the total production, okay? And the rest of the columns are electricity production from different resources, like nuclear, wind, hydroelectric, and so on. So as you can see, there's no particular column named renewable electricity resources. So to do that, we will have to subtract the coal and oil and gas electricity production from the total. Okay, now let's look at the data types of each column. Except for the date time, the other columns have integer data. So when we do the calculation of TF production minus TF coal minus TF oil and gas, we will have a vector of integer. And we name it as renewable. Let's run this and see the time plot. So this is the time plot of electricity production from renewable energy resources in Romania from 2019 to 2024 April. Since we want to predict the electricity production in the last quarter of 2023, we don't need the 2024 bit. Okay, so we're going to discard the data starting from 2024 January 1st and afterwards. We'll do that in a moment. Okay, but now first, to compare the electricity production from renewable energy resources to the total, I make a little plot here. And then this visualization is to visualize the breakdown of electricity production from each resource. So your nuclear, wind, hydroelectric, and so on. Okay, now let's do some preprocessing. So to be consistent with the API of neural forecast, especially when we want to do something like this, univariate time series forecasting, we need a data set with 3 columns. The first is the main time series itself, named Y by default, and then the timestamp named DS by default, and unique ID. Unique ID is to identify the time series. Now, we already have the main time series named renewable and the time index named date time, but we don't have the unique ID yet, so we need to make a new column in our data set, and I'm going to set the unique ID to be the year. So we can say that, oh, this particular time point is from the time series of 2019 or 2020, like that. And so the output of this cell would be the original data frame plus some additional columns like renewable and unique ID. But we only need 3 columns, right? The main time series, the time index, and the unique ID. So that's why in this cell, I just take 3 columns. Additionally, we don't want the 2024 bit of data. So yeah, we need to get rid of them. I did this to make sure that NBEATS doesn't see the time series as a categorical vector. Sometimes integers are seen as like that, right? I just want to make sure that NBEATS sees the renewable time series as a continuous time series. As for the unique ID, they need an integer. So yeah, we don't need to change the unique ID's data type. And then for the date time, they accept several types, if I remember correctly. So the current data type of date time is already okay, which is date time. And then another type that is acceptable is integer. And I just want to make a little comment about connecting this video to the last video about NHITS, especially because I'm using different libraries for these projects. So in PyTorch forecasting, the library I used in the last video, date time is time ID, and then unique ID is the group ID. Anyway, back to our project. Now this is our data frame so far. It has 3 columns only, and then the names are date time, unique ID, and renewable. And as you can see, the data type of renewable has changed to float. Okay, now the last modification is actually optional, but I just decided to do this just to go with the default, the template, if you will. So I said earlier that the 3 names of the data frame that is in the API is Y, DS, and unique ID. We could have just tell NBEATS to refer Y to renewable and DS the date time, but I just decided to go with the default. And so this is our final data frame. Now let's split the data. First, let's set the variable hour horizon. Our horizon would be a quarter of year. So that's going to be 24 hours times 30 days times 3 months. Okay, we just assume that we have 30 days in a month, even though in reality we do realize that the last quarter of 2023 would be October, November, and December. October and December have 31 days instead of 30. So we will miss 2 days. Okay, but this is just for the illustration purpose. So our horizon will be 2160 to be exact. Okay, and then to explain the cell, I'd like to start from the bottom line, which is real Y here. Real Y is the vector, or sorry, the data frame of the ground truth, if you will. So this is going to have the timestamp from October to December 2023. To generate that prediction, we need a history, right? And I set the history to be twice the horizon. That's why I slice the time series for the history for the task set to be -3 horizon up to minus horizon. You see, like in the classical, like non-temporal or non-time series forecasting problem, the task set would be the input or like the x-axis without the ground truth, right? In time series, the axis would be the history. I hope that makes sense. And then the rest of the data set would be train. So train here is a data frame which includes x and y. Okay, the history and the forecasted value. NBEATS, neural forecast library will divide it by themselves. So we just need to worry about separating the ground truth from the history when it comes to predicting. Now let's look at the shape of each data set. So the train has this many rows, 37,000 rows. And then for the task, it has 4,000 rows. Yeah, twice the horizon. And then real Y has 2160 rows, which is the horizon. And yeah, maybe I should have colored the forecasted value as gray, but I color it blue like this to make sure that because we will plot it again later. Anyway, so the right side of the orange line is the forecast horizon, and the left side of the orange line is the history. So this is what we will see in the test data, and hopefully the trained model can generate this forecast. Okay, now we're finally ready to apply NBEATS. In neural forecast, we can train several models. So in this particular video, I have 4. So in neural forecast, we'll train model 1 and then model 2, 3, and then 4. Okay, first of all, I instantiate 4 models with different hyperparameters, and then I put them in a list. I name the list as our model, and then to make the model that is going to be trained, we use neural forecast, and then we put in our list, our model, and the frequency of the time series that we want to predict. Because we have an hourly time series, the frequency would be h for hourly, and we name it as forecast, FCST. Okay, now let's go through the models. NBEATS 1 is the first model, and with the first model, I just go with the default values. So by default, we will have 3 stacks. Each stack has 1 block only, so we can think of NBEATS 1 has 3 blocks. And then by default, apparently we can combine the generic and interpretability architecture. So the top stack would be identity stack, or the generic architecture. And then the second one would be trend, and the third one would be seasonality. And h is the length of the prediction vector, or the horizon. And then input size is the context length, which is twice the horizon. Okay. The horizon and input size are all the same for all models. Okay, so in NBEATS 2, I want to implement a purely interpretable architecture of NBEATS. So that's why I just set the stacks to be trend and seasonality only. Now, since we have 2 stacks instead of 3, I also need to modify MLP units. MLP units is a list of lists. By default, we will have a list of 3 lists. Okay, each list, each small list represent the MLP units for a particular stack. And then for n harmonics and n polynomials, the default value are actually 2. So this is just the default. But when I Yeah, I still type this because I tried out with several other values earlier and find out that actually 2 is already good enough. In NBEATS 2 we have 2 stacks and each stack has 3 blocks. Why 3? I'm just following the paper. Okay, now let's move on to NBEATS 3. So in NBEATS 3, we have 3 stacks, but we don't have a trend basis stack. So we have seasonality and then identity and identity. Additionally, I increased the total blocks in the first identity stack. So I had this idea after trying out several hyperparameters, and I thought maybe there's no trend at all in this time series because there's no clear upward or downward trend. Or what I thought as a quadratic trend might not even exist actually. So that's why I just challenge the identity basis functions, the generic architectures, to find out the frequency of the time series or the periodicity of the deseasonalized time series. And then NBEATS 4, the last model, is purely generic architecture. So we have identity stacks only, no trend and no seasonality. And then each block has, each stack has 2 blocks. One more hyperparameter I forgot to mention is shared weights. So in NBEATS 2, 3, and 4, I set it to be true. And that's because in the paper, it's mentioned that if the weights across blocks within a stack is shared, the model performance would be better. And by default, it's false. That's why I didn't set anything in NBEATS 1. Okay, let's run this. Now here, actually, we can see the total parameters in each model, but unfortunately, there's no clear
I said that it's the
summary
total parameters. No, it's not the
of
total
which
parameters
layer
at all.
has which size.
It's the shape of the model. So like in TensorFlow, we can print out the diagram of the model and then print the shape of each layer, the input of that layer and the output of that layer. And the same goes for this one.
Now, finally, we're ready to train the model. We will know when a model is finished training and a model is starting training by looking at the GPU memory. Okay, now the training is done. We can move on to the last step, which is forecasting. We will get forecast from each model and return it as a data frame. And this is what we will do. So using the forecast, we will use the predict method and put in the test data and then save it as electricity forecast. Since we have 4 models, we have 4 progress bars like this. Okay, now let's see what is electricity forecast. The forecasts are returned like this. If we have only one model, then it's going to be just up to n bits. But since we have 4 models, each model has their own forecasts. NBEATS, NBEATS 1, NBEATS 2, and NBEATS 3. NBEATS column here represent the forecast for NBEATS 1. The model here, NBEATS 1. Okay. Basically, the first model in our model list. And then the next column in electricity forecast data frame is named NBEATS 1, but that is the prediction from NBEATS 2 model. Would be the forecasted value, and then the next column would be from NBEATS 3. Okay, so yeah, it looks like this. Now let's visualize it and calculate the error. To calculate the error, I need to make an instance of the ME class first. And now, yeah, let's visualize this. Here in this cell though, I set real Y. So earlier when we split the data, I set real Y to be the ground truth data frame. So it was a data frame. But now in this cell, I change it to a series, because here. So from real Y, the data frame real Y earlier, I take the Y column. Actually, well, I just realized this. We don't need this actually. We don't need this part because real Y already has all the horizon rows, right? Wait, let me see. Oops. Oh yeah, now it has changed. Okay. Anyway, I'll fix that code later. But no. Let's run this again. Okay. Yeah. So thankfully we can get this again. The MAE would not change since the real Y hasn't changed at all. Anyway, so these are the plots of the real value and the forecasted values. Okay, the first two here, the top two are from model 1 and 2, and then bottom two are 3 and 4. Okay, judging from the MAE, model 3 is the best because it has the lowest MAE of 567, 567, and then the second best would be from the first model. Model 2 has the interpretable architecture, and it has the highest MAE, while the fourth model has the generic architecture. Well, let's start from the best model, okay? The best model here has no trend basis function. In NBEATS 3, okay, let me take you back to NBEATS 3 here. The stack types are seasonality, identity, identity. There's no trend stack there. So that's quite interesting. Of course, I know that this is the best model only among 4 models, but in my experiments though, this is already quite low.
If we want to find the best model, like the optimum
And then furthermore,
hyperparameter,
even though,
then we can try using
and
auto
then,
and beats. So it works
well,
like
even though we don't
sklearn's
have the
grid
trend
search
basis,
or grid search.
the forecast direction
We
is
give
still going up.
some space, some options of hyperparameter values, and then auto and beats will try to train the model with those combinations of
And although
hyperparameters, and then
we don't have
remove
the
the
trend
error
stack in the
and
third model,
pick the one
the
with
forecast
the
direction is still
lowest
going
error.
up. Well, although we don't have the trend stack in the third model, the forecast direction is still going up, pretty much like the real value. The same happens in the predictions from the first model. And then another thing that I notice is that the predictions from model 1 and model 3 are like, well, like they have fluctuations, but the fluctuations are neat. You know what I'm saying? So it's like they have this median line, the baseline or like the average line, and then they just add some variance up and down, up and down. And for the forecast from model 2 and model 4, so you don't have fluctuations, or maybe just very few fluctuations.
And no upward trend or downward trend. See, the predictions make an almost horizontal line.
Okay, so that's it for today's video. We learned another deep learning model for long-term forecasting, which is NBEATS, and applied it to a real data set. And long-term forecasting like this is actually a real problem. Forecasting problems like this might be useful for electricity company provider or government when they want to plan or like build a new electricity providing company. And one more thing I want to point out is that in the paper of NBEATS and NHITS, the longest horizon in their experiments were around 1,000 only, or maybe less than that. So yeah, I admit this task is a bit stretch for those problems, but it's good to see that the variance of the predictions are not fluctuating like crazy. Um, I'm pretty sure that will happen if we use simpler models, because the variance of the first forecasted value would be accumulated to the future forecasted values. But N hits and N beats somehow, well, of course, with their deep models, they manage to avoid that. Okay, so thank you so much for watching. Don't forget to subscribe, give it a like, and share it to your friends. And I'll see you next time. Bye bye.